Sustainable Engineering and Industrial Technology Conference, Second International Engineering Conference. Theme: Sustainable Engineering and Industrial Technology. Our paper will focus on the sub-themes of the conference, which are engineering design, construction and the built environment, modeling and simulation. Our paper number 30 on the conference is titled Finite Fourier Sine Transform Method for Finding Natural Frequency of Flexural Vibration of Moderately Thick Beams. Authors are Benjamin Okudele Mama, Onyedikachi Aloysius Ogwayamba, Charles Chimoba Ike. I am the presenter, Engineer Dr. Ogwayamba Onyedikachi Aloysius. For this topic under discourse, the keywords are finite Fourier sine transformations, flexural vibration and natural frequencies, and the moderately thick beams. These keywords are needed to be properly discussed as to form the basis for this topic. Finite Fourier transformations. Many boundary value problems can be solved by means of integral transformations, such as the Laplace, finite Fourier sine, cosine transformation, etc. These methods transform a differential equation into an algebraic equation, or they can be used to change a partial differential equation into ordinary differential equation. Al-Khaled in 2018 deposited that the finite Fourier transform method is one of the various analytical techniques in which exact solutions of boundary value problems can be constructed. The transform exists for all bounded piecewise continuous functions over a finite interval. In recent years, of course, the finite Fourier transform method has been applied to a wide class of boundary value problems in many interesting mathematics, physics, chemistry, and engineering. Finite Fourier transform method differs from the usual Fourier transformation method in that the solutions are obtained without performing the inverse Fourier transforms. The question here is, how does finite Fourier transformation works? Let us consider a function f of x. This function could be a differential equation, a partial differential equation, or even a governing differential equation. We denote it by a function f of x. And the requirement here is to transform such a function into a finite Fourier sine transform. How do we execute it? We'll couple this function, which we have said earlier could be a differential equation, partial differential equation, as case may be. We'll couple it with an integral sine of a function. Integral sine of a function. In this case, if we want to get a sine transformation, we'll have to couple this function with an integral sine of a function. If we want to transform this function into a cosine transform, we'll do what? We'll couple it with integral cos function. Like in equation 1 and 2, equation 1 will require to have a sine transformation. The function f of x, which we said could be an ordinary differential equation, a governing differential equation also. is now coupled with a integral sine function, and that makes it a finite Fourier sine transformation. The same thing is applicable for a finite Fourier cosine transformation. So in equation 1 and 2, this function f of s has already been transformed into their finite Fourier transformation. Yes, what if we have a function that is a first derivative function, which we intend to transform using a finite Fourier transformation? Very simple. What we do here is to couple that same function, that first derivative function, with the integral sine function, as is shown in here in equation 3. Now, we will now have to separate the integral sine function that comes with the sine function and conjugate it with the first derivative function, which we want to transform. And later, we apply the normal product rule in differentiation. In this context here, that first derivative function, which we intend to transform with the integral sign there, we'll have to operate that function the way it is to have f of x. Because when you integrate first derivative of a function, you have just the function itself, while keeping the sine function constant. And again, execute the operation within limit, which is from 0 to pi, as case may be. The next we'll do is we'll now subtract. In this case, we'll return the integral sign again and the limits, as well as the result of the execution of the first operation of that first derivative function, which is now f of x. Return it while differentiating the sine function there to have cos nx dx. In this case, n will come out as a constant in the cosine function. Later on, by simplification, you now find out that the first derivative of that function, when it is transformed, gives what we have as equation 3. The same operation is applicable for second derivatives, third derivatives, and the fourth derivative. In the fourth derivative, we are transforming a fourth order differential equation or partial differential equation into a finite sine transformation. So we have it as equation 9. In like manner, we can find the finite Fourier sine and cosine transform of any even order derivative of fss and the value of even order derivative at the endpoints of the intervals. The second key way which we need to look at is the flexural vibration and natural frequency. Of course, vibration is the independent displacement or oscillation of a structure with time. That is, any body, any structure that deforms, deflects with respect to time t, that structure is said to be under a state of vibration. And there could be two types of vibration. One is free or natural vibration. Free or natural vibration is a state in which the exciting object or system which enforces vibration is no longer on the structure. Just like you have a vehicle passing through a bridge. Once the vehicle passes the bridge may no longer be on the bridge, but the bridge will continue to do what? Vibrate. The other types of vibration is force vibration, in which the body or the load which causes the vibration is still on it, constantly causing it. So that case is a case of force vibration. And in vibrations can be measured by a parameter which we refer to as frequency, the number of oscillations per minute or per time, number of oscillations per time. Now, this frequency here in free vibration, its own frequency is termed as natural frequency, while in forced vibration, its own frequency is termed as forced frequency. And the first modal frequency in free vibration is what we now call fundamental natural frequency. While in force vibration, the force modal vibration or oscillation is called the forced frequency or the fundamental forced frequency. The other thing we need to look at here is flexural vibration. What do we mean by flexural vibration? First, flexural has to do with body in bending. If a system is under flexural vibration, it means that that system is deforms under bending. And it can only be applicable to flexural members. Flexural members are members that resist their load by bending. So if a body that resists its load by bending is under vibration, we can term that body as being under flexural vibration. Monolithic beams. Conventionally, a beam is a one-dimensional member whose cross-sectional dimensions are relatively equal, and the longitudinal dimension length is far large, about 8 times that of the cross-sectional dimension. Such a beam is termed as slender beams. And for such a beam, Euler Bernoulli proposed a beam theory, an elastic beam theory, which he used for such analysis of a beam. And the theory has certain assumptions. The beam is elastic, the cross-section is infinitely rigid, and all that and all that. But the question here is, whenever this beam, the longitudinal dimension is no longer about 8 times that of the cross-sectional dimension, that beam is no longer a slender beam, rather it becomes what? A thick beam. More really what? Thick beam. And in that context, the Euler Bernoulli theory can no longer be adequate. It's no longer correct to be able to what? Analyze such a beam. And that's the beam, we say the beam is not only that it is a thick beam, that the beam will begin to develop some shear deformations. And these shear deformations are not covered by the assumption made in Euler Bernoulli. So for monolithic beams, the Euler Bernoulli beam theory are no longer efficient for analysis of such a beam. That led us to researchers to work on Timoshenko, first order shear deformation, Reddy's, Milan, shear deformation, and all that. So these theories are capable of analyzing a monolithic beam. So having understand the basics, the keywords in our discussion, we'll now look at what we intend to do. We'll now have to solve a problem of monolithic beam under flexural vibration. Monolithic beam under flexural vibration, meaning that we'll have to consider those theorems that took care of the shear deformation. Shimpi et al. Used the shear deformation theory to develop equation level, where he now put up a governing differential equation for the flexural vibration of a thick beam. This equation level, we are going to see how we use finite Fourier transformation to solve the problem. Figure 3 shows a thick beam under self-excitation. The load that is under free vibration. Now, for a simply supported monolithic beams, both and simply supported, equation 12 is a shape function that defines the profile of such a beam under this sinusoidal excitation. And this shape profile is now superimposed into equation 11 to be able to further define the governing differential equation of that beam. Remember, in equation 11, the right-hand side has a lodal function. Because that we are discussing a free vibration, that lodal function will be equated to 0. That was why in equation 13, it is equated to 0, because the lodal function is what? It's no longer there. Now, we can now apply the finite Fourier sine and cosine transformation, because equation 13 becomes our function under this course. So we are propelling this equation 13 with a sine function, an integral sine function as shown in the screen here. That integral sine function is coupled with our defined equation 13. These functions are further solved as explained in equation 1 through 4, equal evaluated for the limits of integral limits, and after which we'll have what we have in the screen as equation 13. Now for n equals to 1, here we are considering for the fundamental natural frequency, the first modal oscillation, n equals to 1, and for 0 is equal to 0.30. We have what we have here in the screen as equation 15. Now results. Now equation 15 has a parameter lambda 1, which is a non-dimensional parameter that is used to define the behavior, the vibration behavior, that is the frequency of that thick beam. And we'll have compared it for different types of theorem in the Euler-Bernoulli theorem, in the Reddy's Bernoulli beam theorem, and the Timoshenko beam theorem and present work. We evaluated the result of this lambda 1, the frequency parameter, for different types of beam. Between 0. On the first column, between 0.002 to 0.05 is a case of slender beam. You can see the results are almost becoming the same. But immediately you go beyond a slender beam, that's you are approaching thick beam. You are having 0.1 to 0.2, the last two rows. You find out that Timoshenko analysis is still giving us almost the same value, whereas in the Reddy's beam theory and the Timoshenko beam theory at the present work, the values now differ, telling you that Timoshenko beam theory and Reddy's beam theory and present work are almost incorporated this shear deformation, whereas the Euler-Bernoulli theory did not do so. Further again, the result which we obtain in equation 15 is extended for the first, second, third modal oscillation, and results are shown in table 2. Conclusion. What we have concluded here are: 1, that the natural frequency obtained using the present method were identical with results obtained by using the Reddy's method, beam theory method, the Timoshenko beam theory method, because this method, all of them took care of the shear deformation, whereas the Euler-Bernoulli theory did not do so. Secondly, again, for slender beams, the natural frequency were close to natural frequency obtained using the Euler-Bernoulli theorem. But for thick beams, the natural frequency became much more smaller than the natural frequency obtained using the Euler-Bernoulli theorem. The end. Thank you for listening, and God bless you.